Welcome to session number 4. This is the first talk of the session, which will be by Bianca Marchionna, who will be telling us about Stallings-Swan-Dunwoody theorem. So when you're ready.
Thanks, Alex, and thanks for this opportunity to talk. Today I will present a generalization of a theorem that embraces both cohomological aspects and geometric group theoretical aspects of groups, but it's going to be presented in a more general setting. So it's going to be for t.d.l.c groups. So let me first say what I mean with this abbreviation. So it's a family of locally compact groups, LC, that is also totally disconnected. So totally disconnected sounds very scary, but actually means that the connected component are the smallest possible we can get, so the singletons. These are quite wide class of locally compact groups. It generalizes discrete groups, for example, and also profinite groups. So actually, every group can be seen as a topological group with the discrete topology, and actually everything is continuous, every subset is open and closed. So essentially, the theory of absolute group can be translated, say, verbatim to discrete groups, because we are not asking anything more, or whether the topology is so thin that the statements actually are already there. It's a bit more interesting if we zoom out a bit and consider these t.d.l.c groups. There's another important family, a kind of building block of t.d.l.c groups that is made up of profinite groups. So probably you might have in mind, well, the definition of profinite group as an inverse limit of finite groups, but there is also another characterization. So profinite groups are precisely compact and totally disconnected, and of course, compact groups. Some sense, profinite groups play the role of finite groups for discrete groups in the more general theory of t.d.l.c groups. But we will see in a while what actually is the role of profinite groups. Just to have some ideas in mind, well, the examples of t.d.l.c groups that are not discrete and possibly not profinite come from, say, p-adic analysis, for example, QP as an additive group. Of course, also ZP, the p-adic integers, is actually profinite, but also linear groups over, for example, QP, ZP, and so on. But also, there are many examples in geometric group theory. So whenever we consider the group of automorphism, or of a locally finite simplicial complex, for example, a tree, or even a CW complex, provided it's locally finite, then we have like a natural topology, the compact open topology, that makes the group t.d.l.c under my assumption on the automorphism group. So actually, these are the two main areas we can think of them. Let me say again, okay, we are talking about t.d.l.c groups. What we know about their structure. There is still something to understand on their structure, but there are already some encouraging results. And the first one, probably historically, was the following theorem, von Danzig theorem. So it locally describes the structure of every t.d.l.c group as follows. So every t.d.l.c group has a local basis at the unit given by compact open subgroups. That is, whenever we have an open subset containing the unit, we can always find a compact open subgroup, which is kind of remarkable, that is contained into this open set. And just to have an idea, because somehow, I don't know, at the beginning it was not super intuitive to me, but for QP, so QP is an additive group, but the topology of t.d.l.c group is given by the p-adic norm, essentially. And actually, the compact open subgroups are dilations of ZP. And actually, with respect to this norm, these are exactly the balls, the open balls centered at the additive unit, so 0, of radius p to the minus k in this case. So probably we have an idea that in a metric space, balls locally describe the space. And actually, this is a kind of transition example to say, okay, in general, for every t.d.l.c group, compact open subgroups locally describe the group in a neighborhood of 1, but by translation in a neighborhood of every point. So we can sum up this statement with the following slogan. So t.d.l.c groups are locally profinite Why locally profinite? Because these compact open subgroups turn out to be, again, well, compact and also totally disconnected and locally compact. So they're actually profinite. And actually locally profinite means exactly that we have a local basis as here. This locally profineness is used in many areas, for example, geometric group theory, to construct some generalization of Cayley graphs that behaves quite well, even though they are not exactly the Cayley graph we have for discrete groups, but also in cohomology. Let me spend a couple of words on a specific cohomology theory that I'm going to talk about today. So here, probably have a chat. Can we get the recording of this talk? Yes, I think it's already recording. Yeah, thanks. So there are many cohomology theory of t.d.l.c groups that one can consider. Today I will consider probably the closest one to the usual cohomology theory for abstract groups. It is the cohomology theory with coefficients in discrete QG models. So what I mean with this, so I mean a Q vector space with the discrete topology. And our relevant t.d.l.c group is acting on this continuously. That one can prove it's the same as saying that the stabilizers of G on M are open. So open stabilizers will be a kind of key word that is going to be frequent in this talk. I will call the QG the category of discrete QG models. Why discrete QG models? Well, they are particular topological models which form a category which is particularly nice behaved for cohomology. That is, well, there is a result of Castellano and Weigel. They prove that, okay, this category is well behaved for doing commutative algebra, it's an abelian category, but it also has two other properties, enough injectives, enough projectives. So whatever it means, we can actually compute and work with cohomology groups of G in a quite similar way as we do for like the abstract cohomology theory on QG models. One may wonder why Q. It's actually in the proof of enough projectives. That is a generalization of having that every model is a quotient of a free model. It's a bit more general, but actually enough projectives allows us to compute it in a reasonable way. Q can be replaced by any field of zero characteristic, but without loss of generality, I will just take Q. So it's a nice category, and in particular, we can define a family of functors, the cohomology functors, labeled by a negative integer, and called the cohomology of G. It takes any discrete QG model and produces a vector space. And among the invariants we can consider, we can again consider the rational discrete cohomological dimension of our group, which is the supremum of all the indices of this cohomology functor, such that the Cave cohomology functor is non-vanishing in some discrete QG model. So it's a cohomological invariant of the group, but the hope is that we can use it to, say, partially classify our group. This is a very ambitious goal, but there are already some encouraging results already for discrete groups. So for discrete groups, we call that having rational cohomological dimension 0 equals to us that our group is finite. And the nice fact is that also in this more general setting, Castellano and Weigel proved that this also holds with, say, the given modifications also for t.d.l.c groups. It is, a t.d.l.c group has rational discrete cohomological dimension 0 exactly when it's profinite. And note that this is exactly a generalization of the previous result here, because if our t.d.l.c group is in particular discrete, being profinite is equivalent to being finite. So actually, it seems to be quite parallel, but now one can ask, what about cohomological dimension 1? So this is a bit harder, but there is a quite deep theorem that's, for simplicity, I will state it for finitely generated groups, that characterizes when a group, this given group, has a rational cohomological dimension at most 1. Well, we know when it is 0. Let me state it as it is a bit simpler with at most 1. So it is most 1 if and only if the group is virtually free. And this is a combination of two famous theorems by Stallings and Swan. Actually, 10 years later, Dunwoody proved that, okay, these two conditions are in turn equivalent to another more geometric condition. That is, our relevant group acts on an empty tree, so a tree with at least one vertex, and the action has two properties. It's proper, that is, as finite stabilizers, and also, say, cocompactly, so there are finitely many orbits on vertices and edges of our tree. So sometimes it's called geometric action on a tree, but it depends on the conventions. But in any case, we have both a structural and a geometric characterization of a specific behavior of cohomological invariant. And the question is, can we do the same also for this more general theory of t.d.l.c groups? But first of all, we have to somehow clarify at least what we know, what we are going to replace, what is virtually freeness in the t.d.l.c case. Because actually, if we have a t.d.l.c group which is virtually free, essentially the group is discrete. So we would like to have results that also holds for non-discrete t.d.l.c groups. So there is a notion, that is the notion of having a free lattice, that seems to be quite the good generalization, let's say. What is a free lattice is a discrete subgroup which is free, and the closed space has a finite volume that is a finite non-zero Radon measure that has finite mass and positive mass. So in particular, if our group is discrete, it means that we have a free subgroup finite index. So it seems really virtually freeness, but in a more general case, actually we can define free lattices for locally compact groups, but the problem is that we also need that they are unimodular, which is a condition, it's an analytic condition on the Haar measure of these groups that is always satisfied when the group is discrete, so it was somehow silent in the previous case, but is not super general. So there are some locally compact groups that are not unimodular, even some compactly generated t.d.l.c groups that are not unimodular, but somehow it seems to be an hypothesis that we have to add in our generalization in order to get exactly the three equivalences before. And now, okay, let me mention another encouraging results in this attempt of generalization, which is due to Kuhn and Müller. And they proved that, okay, having a free lattice in our given, for our given G is equivalent to have that G acts on an empty tree, again, with the two nice properties, so properly and cocompactly. Cocompactly means the same, so we finitely many orbits on vertices and on edges. And now, since we are dealing with a topological group, properly means that we have compact open stabilizers, I mean more precisely vertex stabilizers. So again, if the group is discrete, compact open vertex stabilizers means finite stabilizers. So actually we get what we had before. And now what we recently proved with Castellano and Weigel is that, okay, these two conditions are in turn equivalent to have rational discrete cohomological dimension at most one. Actually, the proof that is for the discrete groups used some peculiar properties of discrete groups that we couldn't replace. So we had to somehow change our strategy. And actually our argument works also assuming another hypothesis that is already a silent hypothesis for discrete groups, that is the following. So we take U, any compact open subgroup, we fix any measure, Haar measure mu, and we consider all the measures of compact open subgroups. And we ask that this set is uniformly upper bounded, let's say by this norm of G in respect to mu. So we expect that given a unimodular compactly generated t.d.l.c group with this cohomological condition, then this is already true, but we don't have a proof. And actually the discrete case is true, but the proof cannot be generalized. So actually it uses Stallings-Swan theorem, but we want to generalize this. So somehow it's an open question that I will recall at the end. So having the second statement, well, the third statement can be deduced, let's say, in a quite standard way, once we know the theory of Castellano and Weigel. What we actually had to prove is that the third statement implies the second. And now I would like to sketch a bit some ideas of the proof, more because I would like to enlighten some maybe difficulties or some problems that one can deal with while generalizing results from discrete groups to t.d.l.c groups. So here in orange, I just recall what we have to prove, but what is the part of the proof that we are going to focus on now. But I will go back later, so don't worry. Now I just focus on a slightly more general case, and then we go exactly to this statement. So it is worth mentioning that if we have in general a compactly generated t.d.l.c group with rational cohomological dimension at most 1, either the group is compact or we have a specific splitting. So we say that G splits non-trivially over U, where U is a compact open subgroup. And I mean that there exists a compact open subgroup U such that either our G is topologically isomorphic to a free amalgamated product with amalgamating subgroup U over U, or G is topologically isomorphic to an H&N extension, and we call the so-called edge group U again. Why non-trivially? Non-trivial means that U embeds in the first case both as an open subgroup of, in strictly proper subgroup of X and Y, and in the second case, U embeds as an open and proper subgroup of X. So just to sum up, if we are even in a slightly more general case, either the group is compact or the group splits non-trivially over U. Let me stress on the fact that this follows from the decomposition theorem, Stallings decomposition theorem for t.d.l.c groups. And again, you can see that geometric group theory seems to behave quite well. In particular, we have this theorem also for t.d.l.c groups. But let me also observe that if we have this non-trivial splitting, the factors, so x and y and x in the second case, again have the same hypothesis of G. So they are still compactly generated t.d.l.c groups, in fact, open subgroups of G. And also the rational cohomological dimension is at most the rational cohomological dimension of G, and so at most 1. So again, either they are compact or they split non-trivially. And we can somehow continue splitting factors, creating processes of decompositions. We have more than one. Let me give an example. So let's assume that G is non-compact. Actually, because if G is compact, G acts properly and co-compactly on point 3, that is, so we have that thesis. So we can consider G non-compact. Let's assume that G splits non-trivially, let's say as an H&N extension, U is compact. And okay, if X is compact, we can just take the universal Basler tree of this decomposition, and then we get the hypothesis. Otherwise, X splits non-trivially. And let's say as a free amalgamated product, U1 is still compact in X, compact open in X, and one proves it's also compact open in U. So it's fine, it's a fine edge group as well as U. And then we have Y1 and X1, and either they're compact or they split non-trivially. Let's assume that Y1 is compact for a moment, and let's assume that X1 again splits. But now it splits in a strange way. So one of the two factors, let's say here in blue, are U1, so it equals the edge group. So up to isomorphism, we can say simplify these decompositions so that somehow U1 disappears. Here I'm a bit hand waving, but there is a precise way to see this. Actually we have, again, two factors. U2 is smaller than the previous. Here we lost this U1 as an edge group. And the number of factors between the second and the third step still the same. So here we got one new factor, here is the same, because we had this kind of simplification. Somehow at each step we want to do the decomposition of the non-compact factors and then simplify if we can. We stop the decomposition if all the factors are compact. And one proves that our group G satisfies the final statement that we want to get, so X properly and completely on an empty tree, if and only if there exists a process of decomposition that stops after finally many steps. The problem is that somehow we have these possible simplifications. So the number of factors non-decreases at each step, but they might be the same. And precisely when we have this kind of simplifications. And what happens when we start having a sequence of simplifications of this kind? So let me say G is X1 u1, x2, u2, and all the edge groups are strictly, well, form strictly decreasing sequence of compact open subgroups. Well, if we are in discrete case, the UI are finite, so after finitely many steps, because of cardinality, we can say, okay, after finitely many steps, we can stop this kind of degenerate decomposition. For infinite profinite groups, in general, we might have an infinite chain of strictly open subgroups, strictly decreasing. Just to have an idea for ZP, we might have PZP, P squared ZP, P and ZP. So in general, for infinite profinite groups, we cannot exclude that after finitely many steps, this kind of degenerate process ends. But in this particular setting, so the setting we're working with, we can still exclude this degenerate behavior in infinite many steps, because we can use the Euler characteristic. So it's another invariant, cohomological invariant of the group that is defined, okay, if G is compactly generated, t.d.l.c, unimodular, and let's say with rational cohomological dimension at most 1. Actually, there is a more general definition, well, a more general setting where we can define this, but within unimodular t.d.l.c groups. And for example, assume that G, okay, this is a very specific case. Sometimes this infinite decomposition might appear in more than one step. So it's a bit more, I'm doing a kind of simplification, but we're somehow want to just explain some ideas, probably simplified. So let's assume that G has a chain of decomposition as here above. At each step n, so G is isomorphic to the free amalgamated product of xn and y, and un is compact, xn is non-compact, y can be anything. Now with the Euler characteristic, we can say that the Euler characteristic of G is an invariant defined for every R measure mu that we fix. Well, this invariant is the sum of the invariants of the two factors, so xn and y. Here, actually, mu is not exactly mu, but mu restricted to the xn. I just wrote it without the labels, just to simplify a bit the notation, but okay, we have this, minus the Euler characteristic of the edge group, which is 1 minus 1 over the measure of un. This is because un is compact. And now, okay, this holds for every n, and we prove using actually a bit of functional analysis that whenever we have a non-compact t.d.l.c group of which is compactly generated unimodular and has rational cohomological dimension at 1, at most 1, the Euler characteristic is non-positive. So this is at most 0. This is something finite and fixed, and this goes to minus infinity as n goes to plus infinity. But this is impossible. So if we have infinite many decomposition of this kind, then a finite real number equals something that goes to minus infinity. That is impossible. So what we say, probably I oversimplified a bit some steps, but one can prove more precisely that in every process of decomposition, as I said before, the number of factors eventually strictly increases up to pass into a subsequence of steps. And so how to conclude this? So recall that we want to prove that if our compactly generated t.d.l.c group, this is unimodular and is rational cohomological dimension at most 1, and this norm, which is finite, we want to find a process that ends after finitely many steps. And again, let me give a strong simplification. Let's assume that our G admits only one possible decomposition. So x1, u1, and then u, and then y1. Y1, let's assume is compact, and x1 not. So it decomposes in, again, strong assumption, it decomposes in this way. So x2, u2, y2, and assume that y2 is compact. And assume that the process of the only process of decomposition that occurs as the m step, which is we have only one factor, xn, which is non-compact, and the other are compact. And we have this kind of trio of groups. This is a strong simplification, but I just want to convey on the main idea. So whenever you have a decomposition, for example, of this kind, we can somehow say that after finitely many step, we have to stop. Because if we have an infinite sequence of decompositions like this, at each step n, we can again use this isomorphism and apply the Euler characteristic. and say that the Euler characteristic of G, which is a finite real number, is the sum of the Euler characteristic of the factors, and then the sum, well, which is the Euler characteristic of Xn plus the sum of all the Euler characteristic of the Yi, but this is 1 over the mu of Yi. Okay, it's a positive real number, and minus the sum of all the edges. So the Euler characteristic of the edges, which is minus the sum of 1 over the mu I. And now we are about to conclude because Yi, well, contains Ui as a proper subgroup, and this measure splits as an index, as a multiple of mu of Ui, sorry. And the index is at least 2, because again, we are assuming that Ui is properly embedded in Yi. And then using basic arguments, this is at most minus 1 over twice the measure of mu I. This is again at most 0, thanks to the theorem that we proved. And then overall, the Euler characteristic of G is at most minus the sum of 1 over twice the mu I. And now we use the hypothesis, the norm of G is greater than the measure of every Ui. And so we end up having that the Euler characteristic of G is at most minus n, the n step, over a quantity that is determined by G. And so we end up having that, well, let's say if G has this only decomposition, then after finitely many steps, we have to end up. So it's impossible to assume that Xn is always non-compact. Of course, the result is, well, the argument is a bit more complicated, but I just wanted to convey this, how to use the Euler characteristic of another cohomological invariant to actually deduce a structural property of the group. And okay, just mentioned that might be easy, but I want to thank you because my time is up. Thanks.
Okay, let's thank Bianca. Are there any questions for the speaker? Any quick questions?
Is this like process somewhat algorithmical? Like if you start with a t.d.l.c group that has like cohomological dimension 1, and I mean, it seems like your step, like, you know, when you have to stop, right? You have a bound, right? So you can build the actual tree, right?
Yes, exactly. It's the at the end when the process stops, it's just the universal master tree. In general, we can say we can somehow create a bound in terms of the Euler characteristic. I just go back. Well, let's say for example here, so n is the number of steps you have done so far, and okay, the Euler characteristic of G is proved to be non-positive if G is non-compact, and then yeah, we can somehow here, okay, we have a minus, so n. So if we well, so n is at most minus.
Yes. Yeah.
Exactly. So yeah, so this is okay. The quickest question. In general, t.d.l.c groups are a bit. So it's hard to predict a bit which kind of process we might have. So I can say that we have this upper bound in terms of the Euler characteristic, but I'm afraid not much more because they are usually uncountable groups. So it's usually hard to somehow describe them, say, algorithmically. Well, okay, that's maybe it's also my limit, but so I don't have an example in which we take a t.d.l.c group with the hypothesis, we don't know whether it is compact or not, and we check implementing somehow the process of successive decomposition, we check how many steps we need, the minimum number of steps that we need. It would be nice for the moment, also probably because I don't know enough. I don't know, because another problem is that usually we start with groups that we already know that have this property given the hypothesis. So but it's hard to find examples that for which we know this, but we don't know this. But
I see. Thank you.
Very fair question. No, thanks a lot for the question.